Hi, UQCS. So today we've got Dr. Cristina Cifuentes from Oracle Labs Australia to come give us a wonderful talk on Oracle Parfait. Oracle Parfait is a static code analysis tool that looks into scalability and precision of detecting bugs in really large source codes, and she was a principal investigator of this project. So let's give it up for now, Dr. Cifuentes.
Thank you, Sunny. And thank you for inviting me to give this talk to UQCS. I'm going to share some slides. Feel free to send questions through the chat on YouTube. Okay. So today I want to talk to you about Oracle Parfait, the flavor of real-world vulnerability detection. This project I started 13 years ago. And at the time, we were part of Sun Microsystems. So the most important code base in our company was the Solaris operating system, which used to be 6 million lines of code back then. And the idea of being able to run a tool, a static analysis tool over 6 million lines of code really came about because many developers were seeing that there were a few new tools in the marketplace. However, they were taking a long time to run, and many of them were reporting many false positives. So we thought, oh, well, we're part of a research lab. We can research into why this is the case so that we can provide tools that are faster, that will scale pretty well to very large code bases, as well as being able to be more precise. And that was like the whole idea for the project. Our focus was C and C++ initially. Since then, we're focusing a lot on other languages as well. So I'll give you a little bit of what were the main highlights throughout these last 13 years. And this is a repeat of a talk that I last gave in November 2018 in London as part of FaceTab. Okay, so today, the Oracle Parfait tool is used by thousands of developers worldwide on a day-to-day basis throughout our company across commercial and open source code bases of multi-million lines of code. And when we started this project back in 2007, we made some key decisions that were part of the design that has really helped us in being able to scale up the analysis. So as you can see, this is a diagram from a long time ago where we had input program, a C program. And the idea was that you would look at your C program and be able to determine where are potential locations where you may have a bug. And that's what we call the potential defect locator. So that you would start with a list of potentially, here's all of the places where a bug actually happens. And the idea here of starting with potential defect locations was that we wanted the tool to be able to scale. So we didn't want to do whole program analysis like you do in a compiler optimizer. What we wanted to do was to focus on those subset of instructions that are relevant for bugs that you're looking at. So to give you an example, if you're coding in C, a common error is buffer overflow. In a buffer overflow, you want to be able to focus on what is the particular index into that buffer that is going to overflow my particular computation. So you want to technically look at any dereference of a buffer. Potentially, it could be a defect. And what we want to know is when is it actually a defect. Okay. And during this design, what you can see here on the right-hand side is that we have an ensemble of different program analysis, PA1, program analysis 1, program analysis 2, and so on. And the idea was that we observed that some bugs are easy to find, right? Like you may have like a short piece of code, and in this piece of code, you can actually see, oh, I know where it is. That's the bug, right? Whereas in other cases, you may need to rely on the index coming through an argument to a particular function that came from another function, and maybe that function, there was some other computation that depended on another variable. So in that case, those bugs are harder to understand, but also harder to find compared to the very localized ones. And so the idea was that rather than using the same type of program analysis for all the different types of bugs, we have this ensemble of program analysis whereby we start with a very cheap analysis, and that's PA1. And this cheap, quick analysis can tell us with certainty in some cases that some of those potential defects are no defects whatsoever, or that they are real defects. And anything else that it doesn't know, it just passes it on to the next program analysis, right? And you keep on doing that until you've run out of different analysis that you've implemented. So that allows us to get scalability, being able to do that. But there's more to it, right? The different layers of analysis that we have is number one, right? That has helped. But even more importantly is the fact that all of the analyses are being computed in a demand-driven way. And what that means is that if we go back to the buffer overflow example, if you have an error, a particular line, like potential defect, now we're interested in knowing what's that index. So we go back, what other statements were dependent on making changes on that index? And we look at those statements, right? And therefore, we're on demand building backwards a slice of the program. And that's the slice that we actually get to analyze. So demand-driven analysis has been very, very powerful in being able to give us scalability for all of our analysis. And you also saw in the diagram that you could parallelize in different ways, right? Like you can have an ensemble of analysis for a particular defect type. You can have different defect types that can run concurrently. But you can also run your analysis based on this concept of executable file, because we actually compile the code into our intermediate representation, and then you could run on all of these different independent pieces of code. Now, precision is achieved by the fact that we keep track of different lists of bugs, right? You saw in the original diagram, we start with the potential bugs list. And as we go through, some of them will go to no bugs and others will go to real bugs. Oh, sorry, I was just reading through one of the message. It's compiled binaries, coverage analysis type of stuff. Yeah, so we actually compile, so the analysis runs in such a way that we have to compile the source code. So we cannot just take like a random binary like Ghidra would do, although we could combine techniques to be able to do that. Okay. Oh, and we're moving conservatively, right? Like when we move from the potential bugs list to the real bugs list, that's always done conservatively. And so that helps in being able to have like the very good precision. If the analysis is not sure, it would always leave this list here of potential defects at the end that doesn't actually get reported back to the user. Now, in terms of the implementation at the front end, we have various different translators. And these are the most popular languages that we deploy throughout Oracle: C, C++, Java, and PL SQL. All of these languages, you can see here that they have their own translator. The C and C++ translator has been built on top of Clang, but it's a modified version of Clang that we've updated to be able to support differences in different compilers. For example, the GCC compiler supports certain things that the Sun Studio compiler doesn't support, and there are other things that the Intel C compiler will support, and so on. So that's why it's a modified version of the Clang translator. For Java, we run our own Java translator, and for PL SQL, we hook into the PL/SQL compiler into the stage that is after the diagonal representation. And out of that, the main important thing is that we create one intermediate representation, and this representation is LVM bitcode, so BC files. Notice though that LVM doesn't support Java and PL/SQL. So what we've done in this representation is that we have metadata that also gets stored into those BC files. So for example, for Java, we need to store the class hierarchy into the metadata that goes into the BC files. And then given this intermediate representation, then we have the actual analysis step per se, which is Parfait finding those bugs through the ensemble of different analyses. And then reports get reported like in textual form, or you can upload them into a database and so on. Now, key to Parfait has been the fact that developers are not going to change their build process for your tool. And so when we started with C, at the time, Makefiles was what was being used. So we basically have a drop-in replacement for the C compiler, and very, very easy to like integrate Parfait there. We did the same for Java and PL/SQL. However, in practice, if you're like a Java developer, you know that these days everyone's using either Maven or Gradle for the most part. And therefore, you need to now integrate in a different way. So here's a little piece of code that actually is like for our Maven plugin. And the Maven plugin is just going to take your Java source, it's going to build it, create the intermediate representation, run Parfait, and upload all of the results, everything orchestrated by the plugin. And for this particular step, like Maven plugin, I can tell you that initially we used to get developers to change their POM file just a little bit, like add this little piece of information here so that you can find Parfait and things like this. These days, this is fully automated now, because if you want to deploy at scale in like a large cloud organization, you need to be able to have everything fully automated. So now it's more like a push button type of integration with the Maven plugin. There's a question on the chat about plans for supporting CLR MSIL. That would be a very good internship project. We're not actually working on that at the moment. Now, to give you an idea about sample analysis that we've implemented, core to any of these tools, there's always going to be data flow analysis and control flow analysis. Data flow analysis, just keeping track of the data, right? Like if you have variable A gets assigned to variable B, and then you add 20 or whatever, what you're trying to track is like, where is the value of variable A going to? And if there are conditions or loops, then the control flow analysis can keep track of that. And you want to do both of those in parallel, concurrently, I mean. Now, for things like buffer overflow detection and integer overflow detection, we also have analyses that are more specialized, like partial evaluation and symbolic analysis, that try to keep tracks of some of the values, of the potential values that you can have in a variable, so that we can more accurately and more quickly be able to determine those type of overflows. Then in general, when you're talking about vulnerabilities and not just only bugs, you want to be able to implement what is known as taint analysis, because taint analysis allows you to keep track of data that is user controllable. And I'll give an example, a simple example on SQL injection, and from there, you'll be able to get an idea as to what taint analysis can really do for you. But you're tracking any input into the program all the way down to where there's a security-sensitive method that is going to be analyzed. And then your leak analysis is doing the inverse of taint analysis. Is basically looking into whether you're making sensitive data available in parts that shouldn't have access to that data, right? So lower privilege parts of the application. And in order, like for us, like being in an industrial research lab, like Oracle Labs, our focus has always been on bugs and vulnerabilities that matter, right? We don't go for the longest set of list of bugs. We just go for what are the ones that really, really matter. Let's implement those ones really well. And so here I've given you some examples for C and C++. It's always the memory related type of issues, right? Your buffer overflows, no pointer dereference use after pre and so on. For the Java platform, so the JDK itself, it's vulnerabilities that perhaps are not well known in terms of their names, but they were widely exploited like back in 2012, 2013, and 14. And I'll give an example of unguarded color-sensitive method in today's talk. For standard Java applications, you have a lot of the very standard type of web vulnerabilities that are seen around the place. SQL injection, cross-site scripting, LDAP injection, XXC, XCE. There's always insecure crypto. This is becoming more and more common these days. And also insecure deserialization. And then for PL SQL, it's mainly focusing on all of your SQL injections and the fact that they could happen as second order SQL injections. So you may be storing untrusted user controllable data into a database, and later on you may be extracting it and the injection happens at that end. Now, the fact that we have like this one intermediate representation for Oracle languages does allow us to start looking into cross-language vulnerabilities. This may happen between the Java and the C native interface through JNI. For example, you may have a buffer overflow in your C code, but the actual value of the index came from user controllable data from the Java code. And similar, you may have issues across the PL SQL C boundary or the Java PL SQL boundaries. So let us look into a small example on detecting SQL injections. And for SQL injections, look, over a period of 5 years, this was data from 2013 to 2017, and that's 4 years. Okay, there were 1,299 CVEs reported over those years. So that's just to say that SQL injection is still a very common vulnerability. It's not just like the cartoon, it's still happening, okay? And this particular piece of code that I'm showing here actually comes from web code, which is a vulnerable application on purpose, but it's a web application. It's mostly for the purposes of educational purposes. But what I want to give you an idea of how our analysis works and how Taint analysis works is that I mentioned initially that you want to do demand-driven analysis. Now, demand-driven analysis means that we're not doing the analysis over everything, we're only doing it over a subset of the code. So we're going to start from this particular statement. In this piece of code, you can see here that I have a statement.execute query that is going to execute, in this case, a query that you can see here, string query, select from, blah, 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 right? So execute query is what we normally call the sink for a particular vulnerability, in this case, SQL injection. It's a security sensitive statement, and we want to start there. That's the equivalent of dereferencing a buffer for buffer overflows. If you're going to do an execute query, that's where we start. From here, we want to know what is this particular query parameter that is being passed. So we're going to go up the code, and we find that query is actually defined by this particular concatenation of strings. Now, in this concatenation, certain information is constant and others are arguments. So we could be going up like username, or we could be going up password. For this particular example, we'll go up password. So where does this password variable come from? It comes from this other statement that it's an invocation over get parser, get raw parameter. Okay, so what is get raw parameter? We need to go and find that particular method. So we find that method, and in that method, the first statement that we see is that there's a request.get parameter values. So whenever you have a statement like this, where we're going to be asking the user for some information, so that means that that particular data is user controllable, and therefore it's considered tainted data. Now the next statements go and look through this piece of code, but they're just checking for boundary conditions, right? But notice that no one's checking about the contents of the actual data that was sent from the user. So there's no sanitization of the string values. And then we're going to return that particular value, so item 0. And so that means that whatever we're returning is a tainted piece of string. So if we go back to our code, what we've basically said is that here in the password line, get raw parameter is returning something that is tainted. That password is used in the query statement. That means that query is also tainted. And then query gets used here in the execute query statement, and therefore that is potentially an SQL injection, because nowhere along the path was there any checks, any sanitization to ensure that the drop tables example is not happening in this case. Okay, so I hope that gives you a little bit of an idea as to how demand-driven analysis works, and also like the whole concept of taint analysis. Now in Parfait, the way that we report these results, we can give you a text trace of all of the steps, but we also give you a graphical trace in the server. And in the server, you would see on the left-hand side, we would go and highlight the values, get parameter values. That's number one, the source of the tainted data. It then gets returned at the end of this particular method. So that is saying that tainted data is being returned. It gets used here in get raw parameter. So that means that it's making password tainted. Password gets used here in query. So that means the query is tainted. And then it ends up being used in the execute query. And hence you have an SQL injection there. And notice that, you know, for this particular example, the trace is short, right? However, in some other examples, we've seen the trace can be 8, 10, 20 different stack frames long. And so this type of graphical representation actually does help developers be able to more quickly understand what the issue is and along which path is it actually happening. So let me give you now an example from the Java platform, okay? And this one was, the example that I'm going to give is like an exploit called GontVB. This was an exploit for 2012 in August. It was like the very first exploit against color-sensitive methods. And the overall issue was that the color-sensitive method was unguarded. So let me give you an idea, a sample of how this works. So first, for anyone that is not familiar with the Java security model, in Java, your security model is access control based. And everything, like the security manager, is going to have several stack frames of everything that is going to be invoked during the application. So that means that if I want permissions, right, the security manager is going to check if I have the right permissions. So for example, if we want to execute a method and that method needs to have permission Q, then all of the frames up to that one need to have that permission Q, because otherwise, if it doesn't, then it means that you don't have the permission to run that particular method. Now, in color-sensitive methods, it's a concept whereby there are certain methods in the JDK proper code where this stack checking process is actually bypassed. And so instead of relying on checking all of the stack frames in an application, a color-sensitive method is always going to check on the immediate colors class loader. So it's going to check on the permissions for that class loader. And for the purposes of illustration, class.forName is a color-sensitive method. And if I do class.forName on the string foo, what class.forName returns for me is the actual class object that is associated with that foo class, okay? So if there's a class in my application that is called foo, class.forName is going to give me the actual object, the actual class object for that foo class, right? So with that in mind, let us look into a little bit of this convv code. And what I've done here on the right-hand side in red is that I've summarized the very first stack frame that was just convv set fields, and that one goes and invokes convv.getClass. And this is the code for getClass. So in the code for getClass, you can see here that we create like a new object, then it stores the parameter into array of object that we had just created. And then we're going to construct an expression. And our local expression, you can see that it's building an expression with class dot for name with the actual argument that was passed into this get class, which for this particular convv exploit, it was sun.awt.sunToolkit. So basically that statement that I have there highlighted in red is building an expression that says class.forName sun.awt.sunToolkit. And what's important to know here is that when you look at the next statement, the next one is actually going to execute this statement, right? Now notice that now we're going to do an execute. Now, what color is execute? Like what permissions? Well, it turns out that expression is part of the JDK, right? And the AWT package that we had sent is a restricted package, so it actually has high privilege. And therefore, when we invoke expression.execute with like a high privilege restricted package, then it means that we get all of the permissions of the JDK. And therefore, from here onwards, this is trusted code. So I'm not going to go through all of the code, but just to show you like the full stack trace. After that third stack frame with the execute, now you see that there's a lot of other methods that get invoked inside of the JDK. And at the end, we end up executing our class.forName. Remember that I said like a color-sensitive method, like class.forName, is always going to rely on the immediate predecessor's class loader. And so in this case, the immediate predecessor's class loader is also trusted because it's part of the JDK, and therefore, we only check up to there, and that's it. It says, sure, you can go ahead. So even though there was vulnerable code here at the bottom, that was not tracked. Now, in practice with color-sensitive methods, what happens if you look at the diagram on the top right-hand side is that your color-sensitive method before it gets executed, it needs to check for certain permissions to be in place. And if those permissions are in place, then the color sensitive method can be executed. Okay? And all of these exploits that happened in 2012, 2013, they were basically making use of the fact that you could have untrusted code that reaches the color sensitive method on some paths where there was no permission check actually issued. Okay. There's also an analogous version of color sensitive methods that they can leak sensitive data. And it's a similar type of analysis. There's a lot of, there were 4 different cases altogether. But in any case, the essence of the matter is that this permission check is definitely needed, and that's what was missing in the analysis. And notice though that through our static analysis, we're able to determine these issues. We did a lot of work with the Java security team in order to be able to fully understand what were the actual underlying issues to be able to develop the analysis that would detect unguarded color sensitive method calls. Now, a more recent type of vulnerability that maybe you guys have also heard about is the Spectre vulnerabilities, like speculative execution type of issues. And I'm going to focus here on variant 1, which was a CVE from 2017. I have here the definitions for Spectre and for Meltdown, which were both, like found one after the other, right, by the same group. Now, the only difference is that with Spectre, here they're checking microprocessors that are using speculative execution and branch prediction. And by that combination, the speculative execution and branch prediction, you may be able to get information through a side channel attack, right? Meltdown is looking into speculative execution and indirect branch prediction, okay? So that one is much, much harder to do with static analysis. However, Spectre, because it's with the direct branch, that one we can look into with static analysis. So for anyone that is not familiar with like base concepts of this Spectre v1, the canonical example is here on the left-hand side, and that's the piece of code that appeared in the paper. But notice that this code, you may have actually a lot of other statements in between. So this is like the minimal example, but you may have other statements in between all of these statements that you're seeing here. Now, key to the issue was the fact that you're going to have a check on an array size. And in this particular check, variable x, that is going to be the index into my first array, that is going to be user controllable, okay? Then notice that we're going to do a dereference on this array, and then we're going to dereference based on that result into a second array to get a particular value. And some of the conditions that needed to be satisfied for this exploit are on the right-hand side. X, right, like the user controllable variable X, needed to be either in a register or on cache, and the value of array1 sub X, right, so the dereference of array1 sub X that in many places was called K, that one needs to be in the cache. And then both the array1 size that I'm checking against, as well as array2, they need to be in RAM. So those are preconditions in order for the exploit to work. So what can we do with static analysis in this case? Notice that we have a branch followed by a load and followed by another load. right? So the base pattern was branch load load. The branch is going to be like the bound of the first array. This offset computed with the first array is going to be, this value is going to be an offset into the second array. And notice that any statements in between here need to not be like an elpens, a member, or an array index, no spec, or any other pattern that is basically going to just flush everything, right? And in our case, you know, for static analysis, you need to have some heuristics to be able to determine if array 2 can actually not be held in one cache line. So that was the branch load load pattern. The other thing that you need to satisfy is the fact that this variable x needs to be user controllable, right? So if it's user controllable, it means that it's going to be tainted in some analysis. And the last condition is that this load load that happens with array 1, array 2, it needs to be reachable from less privileged code in order for like the actual exploit to be effective. So when you think about like this type of code and you think about, for example, the Linux kernel, then you need to map all of those three parts of the exploit that I mentioned: your branch load load, the user controllable offset, and the reachability of the load load. You need to determine like, what does this mean in terms of the code? So let's assume that in green we have, and in gray, we have this trusted code in the Linux kernel, right? Let's say that we identified a branch load load pattern, which is this bit in the green box. Then we need to be able to identify what are going to be like the boundaries that are going to be boundaries that exist between more and less privileged code. And in the case of Linux kernel, then we're going to use the syscalls for that purpose. And so now we need to ensure that X is user controllable. If it's user controllable, it means that it needs to reach one of these APIs that the user can input data into, is going to be reachable into that X. And also notice that the load load from the array 1, array 2 also needs to be reachable. And so that's going to be reachable from a different API down here. And with that, that allows you to be able to have a static analysis that finds Spectre V1 type of issues. And for this work, we actually work with the Linux kernel team to be able to fully understand and deploy the analysis, of course. So to summarize on some of these security issues, right? I've given you 3 different types of examples. You can basically see that, you know, like all of the code that we've been talking about is here at the top, is application code, right? But the application code depends on a library. And the library may depend on a VM if you're running, for example, Java. And that VM depends on a processor, which also depends on a microarchitecture. And the fact is that each of these levels are going to provide a service under certain assumptions, and the level is also going to consume a service with certain expectations. And at those boundaries, there may be issues, right? So for example, between a library and an application, you may have an SQL injection if you don't do sanitization. Or between a library and a VM, you may end up with information leakage if the isolation is not guaranteed. And then between the processor and the microarchitecture, you can get issues like Spectre meltdown. And so all of these issues affect everything that is further up. So now let us focus like briefly on some runtime results. Because we started 13 years ago by saying we need to be scalable, right? And scalability actually was proven very quickly by the use of the demand-driven analysis and the design architecture that I showed you at the start. Now, if we focus on the Linux kernel, Oracle Linux kernel version 5, it has in the order of 16.4 1.5 million lines of C++ code, and this is non-commented lines of code as reported by the slug count tool. We have 30 different types of bug types that we ran over that code base, and the analysis runtime is 15 minutes. So that means that we're able to analyze just over 1 million lines of code per minute in the case of C and C++. So very, very quick. For the Java platform, this was version JDK 8, update 172. There's some code that is written in Java. It's 4.5 million lines of code, and there was 1.5 million lines of C++. In this case, notice that we have 11 analyses for Java, 30 for C++, and we also had 4 specific analyses for the Java C native interface. Running over those 6 million lines of code took 100 minutes. So this one was effectively 61,000 lines of code per minute. And then for an internal web application of close to 5.5 million lines of Java code, back then when I created these slides, we were running against 8 different types of vulnerabilities. This ran in 5.5 minutes, so close to the 1 million lines of code, right? So the tool has proven that it can be very, very quick to be able to report results. What about precision? This chart here shows data from one of our internal organizations. The data was tracked from June 2011 all the way until June 2017. And what I'm showing here is the number of bugs that used to exist in the particular code base when a run of Parfait was initially introduced into that code base. Over time, you can see in June 2011, over time, you can see that that number of bugs starts going down because developers are fixing the issues. However, at some points in time, they go up. Like December 2012, there was a new release of Parfait, there was a new bug type. So that's what creates some of these spikes. Notice that in December 2013, just about everything was fixed. And then it spiked again in November 2014 because we introduced some new bug types that were very specific to that code base. So it was at the request of developers and security that those bug types were introduced, created a spike, but again, over time, all of those reports were being fixed. Notice that the y-axis, I cannot tell you how many bugs, but I mean, this is real data from one of our organizations. So you may say, okay, that was dealing with like a backlog of various different types of bugs in the code base. What if I want to do my analysis every time that I commit? So sure, we can do that. And the way that this is done is that when you do a whole build analysis, you have n number of files that are going to be processed through Parfait to report certain defects. At the same time, we can start storing what we call function summaries for each of those files. And from there, when you then go and commit one file, let's say that your commit is file n, and you only want Parfait to run over that one file, Parfait is going to go and look at your file and say, oh, actually, file n has a dependency on file 2. So I'm going to grab the function summary for file 2 and do the analysis, parsing your code, taking into account the function summary for file 2, and report any defects. And of course, this is going to be much quicker than running over the whole code base. So here's an example for one particular code base. If you do a whole build analysis, it may take you 15 minutes to do like a whole Parfait analysis scan. If you do the commit time, it's going to take you 2 to 5 seconds if it's C or C++ code, and it can take you 10 to 45 seconds if it's Java code. But nevertheless, super quick. It means that that is something that you can actually integrate into your CI/CD process very, very quick. And so to show you like the effectiveness of commit time integration, this is data for the same organization once Parfait was deployed at commit time. And what this is showing is the number of bugs that it has prevented from being introduced into the code base throughout all of those years. Okay. So let me start wrapping up now. What have been the lessons learned for Parfait? First, analysis need to be precise so that developers pay attention to the results, scalable, so that you can actually run the tool on a daily basis, and even more incremental these days so that you can really integrate it at commit time for practical CI/CD integration. Something that helped us in developing Parfait was the fact that throughout the company, we have a lot of development teams. And fine-tuning some of these analyses is always best done with a team that actually understands the code base and that they understand also the vulnerabilities at hand, right? Especially cases like the JDK with unguarded color-sensitive methods. You cannot find a description of that type of vulnerability other than reading our own papers that we wrote after the fact. Now, for usability, you really need to integrate your analysis in such a way that it just makes it seamless into the existing build process. Developers are not going to change the build process for the tool, so therefore you need to integrate into whatever is the most common, popular type of builds that exist. Also for usability purposes, very important that the tool can actually explain why does it think that in a particular line, in a particular file, there is a bug or a vulnerability, right? You need to be able to generate like the trace, the witness, whether it's purely textual or whether you do it with a graphical interface, but be able to really explain it started up here, it came through these different points, and it's actually exposed at this particular piece of line of code. So with those lessons learned, we feel that these are really requirements to be able to successfully deploy a static code analysis tool. The high precision, the fast runtime, the integration into your build system, and the explanation of the results of the analysis. The success metric for us has been the fact that a large number of bugs get fixed by development. And in this world where there's exploited vulnerabilities keeps on growing every year, right? 33,461 for those 4 years that are listed in the slides, but more these days. These vulnerabilities happen over the mainstream languages, Java, C, C++, Python, C#, PHP, and so on. It's really time to focus on precise and scalable and incremental analysis. Thank you.
Thank you for joining us today, Cristina. I'm just going to check on the chat to see if there's any questions. There don't seem to be. So thank you so much for coming. Hopefully everyone got to learn something new. I surely did. I did not realize how much vulnerabilities existed in code. So thank you so much for coming. And yeah.